two bodies, A and B. These two bodies fell from the same height. So these two bodies fell from the same height, and so we can call that height H. They fell from the same height, and the mass of A is 3/4 of that of B. So the mass of A, so for A, the mass of A, MA, is said to be 3/4. And first of all, let's break that down. 3/4 means what? 3 of a quarter. That's 3/4, 3 of a quarter, and then off stands for multiplication. So that is 3 times 1/4, and that's 3/4. So these 3/4. So it says MA is 3/4 of that of B. So the mass of A is 3/4 of the mass of what? B. So another way we can write that is to say the mass of A is 3/4 of mass of B. So we'll convert that off to multiplication again, and then we can see that the mass of A is 3/4 times the mass of B, which gives 3/4 MB. So we can see that the mass of A is 3/4 that of B. Now we are asked to find the ratio of the specific heat capacity of A to that of B, given that both bodies experience the same temperature rise, and the quantity of heat in both bodies on the ground, when they fell to the ground, the quantity of heat which has been obtained while the potential energy was being converted into heat energy has been falling. That quantity of heat for both of the objects is the same. So we say that the temperature rise, which is change in theta, is the same for both bodies. And then so we can say this is the same for both bodies, A and B. And then the quantity of heat present in each of the bodies at the bottom, because they fell from a height. So from this point initial to final, so at the bottom the quantity of heat they possess is the same. So we can say that the Q is also the same. So now how do we represent this in a more simplified and comprehensive way? So let's represent this in terms of the quantities that we require for us to find the specific heat capacity. So the formula that has specific heat capacity is what? Quantity of heat equals mass times specific heat capacity times the what? Change in temperature, or the temperature rise. So since this is the formula that has specific heat capacity which we are looking for, what we do is that we will simply bring out all the quantities present in this formula for each of the objects and analyze what actually happened in each of the objects. So for object A, we have case 1, and for object B, we have case 2. So object A should be here, case 1. Object B should be here, case 2. So in terms of height, okay, let me adjust this so that we can have enough space. So in terms of the height, we are told that they fell from the same height, so we have H ratio H. Then the next thing we can also talk about is the mass. The mass, we are told that the mass of A is 3/4 to that of B. So this is let's say B is M2, so the 3/4 of M2, while B is the M2. So B is the M2, while A is 3/4 of M2. Now we can also talk about the temperature rise. The temperature rise is the same, so we can say we have change in theta ratio, change in theta is the same. So once we have brought out all the quantities that we have present in these equations, and we are good to go. So the last thing we need to bring out now is quantity of heat. So we can see that the height was not even necessary. We could also decide to skip this height. If we didn't want to bring this out, this will not affect our solution because height is not present in that formula up there. So let's bring out the quantity of heat. The quantity of heat, which is Q. We also told that the quantity of heat is the same. Quantity of heat is the same, Q ratio Q. So now at this point we have one more quantity which we have not brought out, and that is the quantity we are looking for, which is the specific heat capacity. Remember, that's the quantity we are looking for. We are asked to find the ratio of the specific heat capacity of A to that of B. So specific heat capacity, since we are asked to find the ratio of A to B, it means that they are different. So let's call the SHC of A to be C1 and that of B to be C2. So we're having C1 ratio C2, and we need to represent this with values, whole number values, so that we can be able to present our answers in terms of the ratio. So what do we do now to get this? Now, going back to that formula which has specific heat capacity in it, that is this. That's specific heat capacity formula, and we have the quantity of heat on the left hand side. So we are going to take that formula and apply it to each of the cases. So for the first case, we are going to have quantity of heat will be equal to what? M1 C1 change in theta, right? And then for the second case, we're going to have quantity of heat will be equal to what? M2 C2 change in theta. So something good is happening here. Because since we are required to find the ratio of C1 to C2. That's what we're asked to find now, the ratio of the specific heat capacity of A to that of B, right? That's what we're asked to find. Now, how do we find the specific heat capacity of A, which is C1? How do we find it? We can find C1 by making C1 the square root of the formula, and that will be C1 equals to Q divided by M1 change in theta. So here we can find C2 by saying Q divided by M2 change in theta. Okay, so since both quantity of heat are actually the same, so what we can do is that we can actually equate this case to this case, because in the first case, which involve object A, the quantity of heat is equal to Q, and in the second case, which involves object B, the quantity of heat is also equal to Q, because we were told that the quantity of heat present in both of the objects when they go to the ground is the same. So for that reason, we can say that at this very point, we are going to come back here. So just keep this down somewhere. We'll come back here, but we are going to work majorly with the equation here, because it's going to be more simpler that way. So we are going to simply say this is equal to this. Why? Because this is equal to this. So since the QA is equal to QB, so we can say M1 C1 change in theta will be equal to what? M2 C2 change in theta. So for that to be true, we can write that as M1 C1 change in theta equals to M2 C2 change in theta. Now, do you know why we are doing this? We are equating the equation in case 1 to that in case 2, because we want to do a comparison between C1 and C2, and we can only do that when both of the equations are connected to each other. When the equations are connected to each other, we can do that easily. But we could have done it, we could have also solved individually, as in we could have found C1 here, assuming we were given direct values for this and the Q as well. If we were given direct values, for example, the Q was 400 joules, and then the temperature rise was 50 degrees Celsius, and then the mass was 50 let's say 50 kg or 5 kg. What we'll simply do is that we'll substitute and find the value of C1, and then we'll do the same thing to find the value of C2, putting the values of the masses and temperature rise and the Q which we are given for case 2. At the end of the day, we can say C1, for example, is equal to 2, and then C2 is equal to 4. So we can say if C1 is equal to 2 and C2 is equal to 4, so it's in a ratio of what? 1:2, because 2 will go here to give 1 and 2 will go here to give 2. 1:2. That's if we are giving values for all the quantities. But now we are not giving values for all the quantities, but rather what we are giving, we are giving values that shows a relationship between case 1 and case 2. How? We are told that the mass of A is 3/4 of the mass of B. So we can see, instead of giving us direct values, we were giving values that shows a relationship between object A and object B. For that reason, we have to equate the two sides. So we have to make A to be equal to B, since the quantity of heat is the same for A and B. So we just use that opportunity to make this side of the equation to be equal to this other side of the equation, so that by doing this, we can now have an expression that will eventually look like this: C1 over C2. This is exactly what we're looking for, ratio, because C1 over C2 is the same thing as saying C1 ratio C2. So if we can have an expression like this, our answer will come out. So let's see how we can have an expression like this: C1 over C2, by equating the two equations in both sides to get to each other, which we have done. So equating the two equations to each other, like what we have seen here, this side is equal to this side. So what we are going to do now is, let's put the values that we are given in the question. So we are told that the mass of A is 3/4 that of what? B, and the specific heat capacity was C1, and the change in temperature was the change in theta. Then for the second side, the mass is M2 and the SHC is C2, and then the temperature rise or temperature change is also change in theta. So from this we can now find a way of writing C1 over C2. So if we want to write something like C1 over C2, how do we do it? First of all, let's make this a bit simpler. To make this a bit simpler, we're going to cancel out, since we're having change in theta on the left hand side and on the right hand side. So let's divide both sides by change in theta. So dividing both sides by change in theta. So this we cancel out this, and this we cancel out this. So eventually we'll be left with 3 over 4 M2 times C1 equals M2 times C2. So that's what we are going to be left with here. And now looking at this equation, since this is what we are left with, how do we write an expression for C1 over C2 from this equation which we're having? How do we write an expression for C1 over C2? Now I want you to understand something so it won't be confusing. Let me illustrate something like this. If we're having A times BD equals to C times FE. Now let's assume this expression will be in fractions before we made them to become linear like this. Let's assume they were in fractions before. So if they were in fraction, how do we actually convert it to make it in a linear form like this? Remember, we always cross multiply. If we cross multiply, if we're having A over FE equals to C over BD, and we cross multiply, what are we going to be having eventually? What we're going to be having is this. On the left hand side we have what? A times BD equals to what? C times FE. So you can see that what we're having here is the same with what we have here. You can see it. So now this means if I am to arrange a linear equation in fractions, if I'm to write it in fractions such that I will get the same thing when I cross multiply, how am I going to do it? I will say this first element divided by this second element equal to this first element divided by what? This second element. That is the only way I can write it, so that when I cross multiply, it will take me back to what I have. Hope you can see this. You can see this beautiful illustration here. So don't let it confuse you when I do what I want to do right now. So going back to what we're having here, we're going to do something similar. We are having an expression like this: 3 over 4 M2 times C1 equals M2 times C2. I want to have an expression for C1 over C2. So how do I transform this equation so that I will write it in fraction? So I'll be having fraction on the left hand side and fraction on the right hand side. So the fraction I want to have on the left hand side, I already know it. That is what? C1 over C2. That's the fraction I want to have, because that's what we asked in the question: the ratio of the specific heat capacity of A to that of B, which is C1 ratio C2, or C1 over C2, just as I have written it down. So that is what I want to be on my left hand side. So if that is on my left hand side, what should be on my right hand side, so that when I cross multiply, it will take me back to exactly this expression that I'm having originally. Now, if I put M2 here, and I cross multiply, will I have C2 M2 coming together? Yes, I will have C2 M2 coming together, which you can see on the right hand side here, C2 M2. So it means that M2 is qualified to stay here. So it will now be M2 over what? What should not be here? So that when I cross multiply, I'll be having the same thing on the left hand side. So it means that 3 over 4 M2 has to be here. 3 over 4 M2 has to be there, so that when I cross multiply, I'll be having C1 times what? I'll be having C1 times 3 over 4 M2. So when I cross multiply, so you can see it with this, the equation has been balanced. It has been arranged properly. So in fraction, I've converted this linear equation now to fraction equation. Good. Now, what we're going to do next is this, because we are actually looking for the ratio of C1 to C2, which is already coming out. So our answer is coming out already. Now I'm going to divide both sides by what? M2, because M2 is common. So M2 cancel out M2. So I'll be having C1 over C2 equals to what? 1. When M2 cancels M2 here, I've left it 1. So 1 over what? 3 over 4. Now this other M2 has turned to 1, so times 1. So that means we are going to be having C1 over C2 equals to what? 1 over what? 3 over 4. So this simply means C1 is 1, C2 is what? 3 over 4. That's what it means. So when C1 is equal to 1, C2 will be what? 3 over 4. We can see the ratio has come out already, but we are still having fraction in the denominator. We don't want to have fraction in the denominator. We want to have whole numbers. So what do we do to transform it further so that we can have whole number ratios? Now I will convert this fraction into another kind of fraction, so that the denominator will no longer be a fraction. The denominator will be a whole number. So I will write it like this: 1 divided by 3 over 4. 1 divided by 3 over 4. So we can convert this to what? 1 times 4 over 3. 1 times 4 over 3 is what? 4 over 3. So it means another way of writing that fraction is to say C1 over C2 is equal to what? 4 over 3. So you can see it now. When C1 is equal to 4, C2 will be what? Equal to 3. So from here, the ratio of C1 to C2 is what? So you can say C1 ratio C2 is what? Equal to what? 4 ratio 3. So this is the answer. So the ratio of C1 to C2, which is the specific heat capacity of object A to that of object B, is actually 4 ratio 3. 4 ratio 3. Now to be sure that what we have done is correct, when you punch 4 ratio 3 with your calculator, that is 4 over 3, when you type 4 over 3 in your calculator, it will give you 1.3333 and so on, recurring theory. And when you also type this 1, when you type this 1 over 3 over 4 with your calculator, you also have what? 1.3333 recurring theory. So that tells you that what we did here was only a transformation to remove the fraction from the denominator, but it still actually means the same thing. So 1 over 3 over 4, 1 over 3 over 4 is the same thing as what? 4 over 3. So another way we can write this is to say C1 ratio C2 is also equal to what? 1 ratio 3 over 4, or 1 ratio 0.75. But if you want to write your answer in whole number form, then this is the answer in whole number form. So that is the solution to this question. So you can attempt other questions that are similar to these ones, where you have to find the ratio of one quantity to another, to the same quantity, but in another case. So at times physics questions can be interesting like this. You will have the same thing happening in two cases. The same thing it could happen in motion. It could be in the form of a motion question, or heat question, or even electricity. You have the same thing happening in two cases, and then you will be asked to find, you'll be given some things in common, some things that are common between the two cases. Then you'll be expected to draw a relationship between the two cases, and then find the ratio of that particular quantity in the first case to that same quantity in the second case. So this is exactly how to go about such questions. You bring out the analysis of the quantities like this, and then you find a way to equate the equation of the first case to that in the second case, and you do that by looking for what is common between the first case and the second case. Once you can find what is common, then you can make that the subject of the formula, just like Q was made the subject of the formula, and then you can now equate the equation in the first case to that of the second case, and you make sure that the quantity which you are asked to find is present in that equation which you have equated in both cases, so that you can now bring out a ratio which is like what we have here now, C1 over C2. You are bringing it out from the equations which you have equated to each other. So you now have a ratio C1 over C2 in such a way that when you cross multiply it, it will lead you back to that particular equation which you are coming from, and from there you can now cancel out anything to cancel out, and then do some little arithmetics to convert it to a normal fraction, like an improper fraction, so that you can be having whole number ratios like 1:2, or 2:4, or 5:10, as the case may be. And also you need to also note that when we have something like 4:3, we can also multiply each side by 2. So if you multiply this by 2, it will lead us to what? 8. And if you multiply this by 2, it will lead us to what? 6. So we can also say this is 8:6. And we can also as well say is what? 16:12. So any one of them you find your options will be the answer. Hope that's clear. All right, that's good.